Hello, my name is Amy and welcome to my Dissertation Conference video. My dissertation topic is about agrivoltaic systems and the potential for these to be implemented in the UK by looking at the Isle of Wight as a case study. Agrivoltaic systems are a fairly new form of land use where soil-grown crops are combined with PV panels. The first study to assess this performance was conducted by Duprez et al. In Montpellier, France, where solar panels were mounted 4 metres above the ground with the pillars 6.4 metres apart, and the experiment determined that land productivity was not reduced. In terms of crop growth beneath the pillars, extensive literature provides evidence that despite the reduction in solar radiation and soil temperature, it is possible to cultivate high-quality crops. And as it says on the slide, it is estimated that 2,200 systems have been installed worldwide since 2014. The justification for why I am looking at the implementation of such systems in the UK stems from the fact that anthropogenic concentrations of greenhouse gases have increased to unprecedented levels, and as such, Britain aims to reach net zero carbon emissions by 2050. So in order to do so, large areas of land will be needed for photovoltaic farms for electricity generation. However, in the UK, 83% of land is currently devoted to agricultural or forest uses, and so there's a competition between energy and food systems. So agrivoltaic systems provide an opportunity to alleviate this competition, and again, going back to that first study in France, it was found that AV systems have the potential to increase global land productivity by 35 to 73%. The Isle of Wight is also a justified study site as it has a high photovoltaic power potential due to its increased southerly radiation, as can be seen on this image. The Isle of Wight also has 35,000 hectares of agricultural land, and the island also grows a large variety of crops on it, and so this allows my analysis to include assessing the efficiency of agrivoltaic systems over multiple crop types. In undertaking this thesis, I will aim to answer two specific research questions. The first will be what area of land on the Isle of Wight is suitable for solar energy production through solar farms. This will be answered by the first of my methodological objectives, which is to conduct a site suitability assessment to identify suitable locations on the Isle of Wight for solar farms. The second question is, would the implementation of agrivoltaic systems result in a yield advantage for both energy and crop production? This will be done by the second objective, which is to calculate the land equivalent ratio for agricultural land selected in the analysis, which will determine the efficiency of the system, and I will go more into this equation with my method. The first part of my method, conducting the site suitability analysis, involves undertaking a GIS multi-criteria analysis to identify areas on the Isle of Wight that are suitable for solar farms. I have chosen to do this first as it allows for an assessment of how suitable the Isle of Wight is for solar farm development and where such developments could be placed. 5 criteria will be used as shown in the table, and each individual layer will be made first in line with the requirements derived from literature, and then they will be overlain. I have chosen to do a Boolean MCA where areas that meet the requirements in the table and are therefore suitable are given a value of 1, and everywhere that isn't is given a value of 0. This means that when overlain, locations provided are entirely suitable for solar farm development. This here on the slide is the original table that I used in my proposal, but red now indicates where data or my data source has changed from my proposal. Once I have conducted the multi-criteria analysis and have suitable locations for solar farm development, I will then use an equation called the land equivalent ratio to help assess the efficiency of potential agrivoltaic sites. I will use the crop map of England as shown on the slide to select different crops and overlay these polygons with a suitable layer to identify areas suitable for solar farm placement for each crop type. Using average statistics from DEFRA and literature, I will then calculate the LER for each crop, which is the yield under agrivoltaic conditions divided by the yield in a single system, plus the agrivoltaic electricity yield divided by the yield of a normal PV plant for this area. A value greater than 1 indicates that a mixed system is advantageous for both electricity and crop yield in comparison to single systems in the same size area. I will now discuss what I have done and my results so far. So briefly, this slide presents my individual criteria layers for the multi-criteria analysis. The top left is slope and aspect layer, where green areas valued 1 display where slope is less than 10% and aspect is southeast to southwest facing. The top right is solar radiation, green presenting areas that receive 1,050,000 watt-hours per metre squared per year or more. The bottom left is all areas within 100 metres of residential areas, and the bottom right is all areas within 10,000 metres of a 30 kilowatt power line. The result of the multi-criteria analysis is this map on the left, which details all areas in the Isle of Wight suitable for solar farm installation in line with my criteria. Then on the right is all areas from the suitability map that also overlay with the crop map shown previously. This result shows that 41 kilometres squared and 10% of the Isle of Wight is made up of cropland that is suitable for solar panel farms, and so 10% of the Isle of Wight is suitable for agrivoltaic installation. Furthermore, this map on the left shows the overall suitability in pink and the cropland suitability in blue to show just how much cropland contributes as suitable land for PV power production, and hence why this research is so justified. On the right, I've selected cropland suitable excluding grass, so this is just arable and horticultural land, and the area is still 17 kilometres squared, so it's still really substantial. The previous figure, however, is just as important, that it does include grassland, so that was the 41 kilometres squared. As grass is listed by the government as grade 3B agricultural land, and at the moment grades 1 to 3 would normally be considered unsuitable for PV installation due to their agricultural status. Post multi-criteria analysis, I have then looked into individual crop types further. I've done this process for a number of crop types now, but I will give the example of wheat here. So firstly, using the crop map 2020, I have selected wheat layers and overlaid this with the suitability layer to give wheat areas suitable for solar farms. This layer can be seen on the slide. However, as you can see, there are a lot of small polygons which would not be viable for solar farms. Therefore, I have selected polygons with areas greater than 40,000 metres squared, which is the equivalent to 10 hectares. This is justified as from research I found that 5 hectares is generally needed in the UK to produce 1 megawatt of power. And so I've kind of looked into solar farms generating 1 megawatt, and so I've doubled this area to account for AV systems. I've then verified each polygon using Google imagery to check it is actually suitable. So for wheat, 24 out of 31 polygons were accepted. The other 7 were not due to forest and road cover not seen in the map layer covering the polygon, so it was actually really worth checking just to verify these areas. The total area suitable was calculated as 1.9 kilometres squared. I then converted this to hectares and multiplied it by 7 in line with government DEFRA average crop yield statistics, which state wheat yield for 2020 as 7 tonnes per hectare. I've then deducted this by 8% in line with the yield reduction for wheat under agrivoltaic systems identified by Dupas et al. To get an AV yield of 1,252 tonnes per year. I have also identified the solar radiation of each polygon and calculated the PV power, which is done by area size times solar radiation times PV efficiency. This value has then been multiplied by 0.52 to give an agrivoltaic power potential if the panels were at half yield. This has then been divided by 8,760, the hours in a year, to get capacity of 38 megawatts. It's estimated that solar farm capacity on the Isle of Wight is currently only 70 megawatts, so even just by looking at wheat, this shows a massive potential for expansion. It also suggests that this could power 11,000 homes per year. I've then calculated the land equivalent ratio for wheat using the equation and the value stated. The result was a value of 1.44, meaning that 144 hectares would be needed for single systems of wheat and solar farms to be as productive as 100 hectares in a dual agrivoltaic system. To touch on problems encountered so far, I had issues accessing the land cover map from Medina and had issues with the data source. Owen MacDonald managed to very kindly sort this for me on a newer version of ArcGIS Pro and upload the layer to NetData, which I could then access it from. I also could not access the open infrastructure map in ArcGIS as planned in my proposal, but I've instead used a powerline layer on ArcGIS Online. One problem I'm having at the moment is the crop yield values for agrivoltaic reductions. They're not listed extensively in the literature, and I'm struggling to find crop reductions not applicable to wheat or any studies in similar climates to the UK. So for now, my estimations are exactly that. They're big estimations, but I still think it's worth using the LER values and using an approximation of the efficiency of the system, even if it's not necessarily applicable to other crop types or really accurate for the UK. Finally, in terms of next steps, I will continue to manually check each suitable polygon for the differing crop types to get an area suitable for agrivoltaic development for each crop type. I will also continue to read literature to see if I can find more appropriate values for crop yield reduction to use for the LER so they're more accurate. I will also take on board any feedback from the conference and reassess, and then hopefully in December I will start writing. Thank you so much for listening, and I now welcome any questions and feedback.